We are studying the subject of hydrogen storage and the distribution pipeline system. Well, last week we didn't have a in class, but as a homework, you reviewed this several storage method. As you as you guys watch in the YouTube, there are tank, very high pressure tank, and the liquid type and solid types. There are typically three types. So today we like to review them again, and also we like to review the pipeline as well. In YouTube, as you can see that there are so many good real applications and explanations, and these are this is gonna be our lecture materials. We will start. We will. Okay. Okay, this was a handout as a review of hydrogen storages. Well, it has a short abstract regarding this storage technology, but the main point, as shown here in table of content, there are several hydrogen storage methods. First one is the compressed hydrogen storage. As you know, the hydrogen densities are so low. We need one of the most effective methods to increase the density is to compress the hydrogen gas. So this is the most well-known and adopted method to store hydrogen gas. And second method is liquid hydrogen storage. I'd like to open our lecture notes. Well, this phase diagram is very well used to better understand the several different methods of hydrogen storage. So I hope that this should be very clear to you. Well, again, this can be very easily found from internet, but I really hope that you can draw this diagram yourself, indicating how this density is changing along with the temperature and pressure. These several lines show iso pressure line. So as you can see that how the density of the hydrogen is changing along with the temperature and pressure. Now, as you can see here, as a liquid. This is a liquid line. LH2 is only 4 bar. It's not the 1 bar, but slightly 4 bar. Then as you can see that we reach the hydrogen density reach about the 64 or 62 gram per liter. Okay, this is the liquid. And then gas stages, depending on the temperature and the pressure, it varies. As you can see here, as these are room temperatures. It varies from about 10 gram per liter to up to 60 gram per liter. But as you can see that to reach, well, we cannot reach up to 60. We can reach up to 45 at the room temperature. As you can see that we have to press about 880 bar, which is even higher than 700 bar. And to increase further, we can apply the higher pressure, such as 1000 bar. Then we can reach about 50 gram per liter. But as you can see that liquid, we reach the again 62 gram per liter. But the main problem is that we have to lower the temperature as low as the 33 K or minus 253 Celsius, which is extremely low. Oops. So liquid, compressed, and the cryogenic, compressed hydrogen storage. And then, okay, these three methods can be explained in this diagram. And then there is another method, a metal hydride hydrogen storages. We like to watch the video together. And what is the about metal hydride hydrogen storages and chemical hydrogen storages? Well, hydrogen as a hydrogen carrier, methanol and ammonia can be used, and comparative analysis. So, well, as a practical application, this compressed H2 is widely used for transportations. Well, even though this method can be a kind of dangerous, well, not because of a hydrogen gas itself, but the tank can, the internal pressure is as high as 700 bar. That is being used as in the Nexo. So compressed hydrogen storage again is the mostly widely used. Well, short introductions. Hydrogen's potential as a clean energy carrier hinges not just on production, but also on efficient and safe storages. So energy production is important, but also safe storages should be followed. So compressed hydrogen storages, I'm sure you watch this YouTube, and this is a tank. Okay, let's open this one and then watch together. And tank are divided into 4 different groups: type 1, 2, 3, 4. Actually, there are another type as a type 5, which I will further explain. But simply say that we don't have a liner for the hydrogen tank. That's the type 5. Anyhow, these types of the basically compress the hydrogen. This is a gas type. 350 to 700 bar is a gas. High pressure compressed gas. And there are pros and cons. The most important point in the pros is been a mature technology, the commercially available and widely used, and importantly is a very suitable for fuel cell vehicle. But low energy density compared to a liquid, low energy density. What does it mean? Density means the volume, the mass stored with respect to volume is small or less than a liquid. Well, high cost carbon fiber composite tank. Well, these 4 types of a tank are made of a carbon fiber. Why do we need to carbon fiber rather than regular steel? Well, simply if we use the steel, the tank will be very heavy, really heavy, sometimes as heavy as the vehicle itself. So practically, it's not possible to make the tank using metal. So no choice but to use the carbon fiber composite tank, while always a safety concern. Applications and etc. And another important application is the hydrogen refueling station. Well, recently, Hyundai announced that their all new Nexo has been very popular, almost 50,000 vehicle has been sold. I'm not sure the exact number, but the main problem, one of the biggest problem, is the fuel station. There are not many places where we can get the hydrogen fuel. So that is the one of big problems at this point. But we believe we believe that the station will increase. The number of station will increase. Okay. Liquid hydrogen storages. The hydrogen will become a liquid at minus 253. That is the temperature, as you can see in the chart on the left-hand side. And then it become a liquid. But again, what's the density? Density is about the 62 gram per liter. So the key component is the double-walled vacuum insulation tank. Okay, what is a double-walled vacuum insulation tank? Boil-off gas management system. What are these components? Very important to keep the temperature as low as minus 253. So pros and cons, as you can see, high energy density, 62 gram per liter, and essential for aerospace and space launch system, space and launch system, there space-wise, very, I mean, the volume can be very limited. And cons, cost of a high cost, boil-off losses over time, and complex handling and infrastructures. Again, the boil-off means that there cannot be completely insulated. Means that over the time, well, I would say over the days, several days, the heat will transfer into a liquid, and then liquid will become very high, become a gas. Then the pressure will increase. So this liquid tank is not the pressure tank. So the gas has to be released. Otherwise, this tank will explode, or the liquid will leak. So unfortunately, we have to boil off boil off loss over time, and application, and mainly aerospace application. But recently, this liquid application getting a little bit more popular, and compressed cryogenic compressed hydrogen storages. Okay, we already watched this one, but the point is that we have to keep the temperature. Okay, rather than 700. Okay, rather than 700, we can keep the pressure as the 200 to 350. And also hydrogen is cooled. How cool? The temperature will be about the minus 200, and the pressure can be a little bit lower than 700. So then the density is the much higher than others. And metal hydride is store hydrogen, is very importantly absorbing the hydrogen molecule into a solid alloys. This system is very compact and operate very low pressure and the say regular temperature. But the solid alloy itself, it can be very heavy, and the it has a problem to release the hydrogen. It takes some time to release. That's the one of the problems. Anyhow, there are still a lot of research is going on. Why? Because this is a very safe storages. We don't have to worry about the explosion. It's just the hydrogen gas is already inside the metal, and then all you need to is to release the hydrogen from the solid. But again, it's very heavy and so on. Well, no matter what the storage we are using, the most concern is the safety. So if safety is a concern, the metal hydride hydrogen storage has a very bright potential. So while the point is that how to further increase the density, and so that the storage can be lighter. There's still a lot of research is going on. Chemical hydrogen. While chemical hydrogen is stored in the chemical compound and release gas upon the heating or reactions. So there are some chemical carrier and pros hydrogen density, while a little higher hydrogen density and the very safe. Is very safe, and but the problem is we have to have some reaction to become a chemical hydrogens, and well, as applications, military emergency fuel packs, and there are still a lot of research is going on here. And the hydrogen carrier as a methanol and ammonia, this is a very become a popular right now. We use the methanol and ammonia. As you can see, there are H2 hydrogen in there. So using the methanol, we carry the hydrogen, and then we 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 the one of the most important point of this methanol is the liquid at the ambient temperature, at room temperatures. And then whenever we need, we can reform, release hydrogen well, with a CO and CO2 byproduct. Ammonia is certainly is one of a very excellent method, higher hydrogen density than higher hydrogen density than methanol. Can be cracked. We call it cracking. Cracking into hydrogen nitrogen. As you can see, here is the nitrogen and hydrogen. So ammonia itself is a very safe room temperature. So we carry the hydrogen using in the form of the ammonia, and then we cracked into a hydrogen and the nitrogen. But unfortunately, this ammonia can be very toxic and requires very careful handling. Okay, anyhow, I'm sure you already review all these different types of hydrogen storages. As emphasized in the very beginning, hydrogen produce and generation of hydrogen is important, but to use them for useful application, we have to have a method to store them. So storage is the one of the key. Okay, let's go to the YouTube. This is the YouTube channel called All About Sustainability. Well, it's a relatively recently developed. I noticed that this review, the hydrogen storage is very well. So, but this is not the only one. We can have a lot. We can find a lot of further informations about the storage method. Okay.
The form in which the hydrogen is stored determines not only its transportation method but also the ways of hydrogen utilization. In general, hydrogen storage systems can be divided into two categories, physical-based and...
As you can see that H2 storage systems can be divided into two methods. One is the physical-based and the material-based. physical based means that as shown in the chart, the state chart, density, pressure, and temperature. We have three different methods: CH2 and CCH2 and LH2. And the material base means that we kind of combine the H2 into a different material, and then the product now will become safe, and so LOH2 and metals, and this is a power. Cannot see well, but let's see.
Material-based storage. In the former case, the hydrogen is stored by altering its physical state, namely increasing the pressure, compressed gaseous.
Just 1 second, please. Well, we cannot. This is the
hydrogen storage, CGH2, or decreasing the temperature below its evaporation temperature, liquid hydrogen storage, LH2, or using both methods, cryocompressed hydrogen storage, CCH2. In the case of material-based storage, additional materials as carriers are applied. They can bond with hydrogen molecules or atoms, either physically or chemically, and thus enhance storage density and safety as compared with those of physical-based storage systems. In this video, we will be covering physical-based, compressed gaseous hydrogen part. The easiest and most mature way to store hydrogen gas is to compress it and fill it into pressure vessels. There are currently 4 types.
I like to get rid of these captions, but no, this is not the okay. So this video shortly discuss about the CH2 compressed. So to compress, we are using the tank, and there are 4 different types. So metal liner. What does it mean, liner? Liner is the kind of a container, and as directly touch the hydrogen gas. And so metal liner and polymer liner is very important to understand the polymer liner as a type 4. And okay, let me go through.
Available. The choice to use which vessel type is based on the application field with a compromise between technical performance and cost. From a technical point of view, 5 main factors are usually taken into account to characterize the hydrogen storage system. Gravity and cost.
Let me explain a little bit more here. Type 1 tank, there is no other color, just the liner itself. This one, the tank is made of the steel, very thick steel. But again, the steel, the density is really high, so this tank is gonna be heavy. So we can reduce the little bit of a thickness, and in the hoop direction, we are using the carbon fibers. Why only in the hoop, in this cylindrical part, rather than this dome part? Well, this cylinder part, the stress in the hoop direction is twice as big as the, in the cylinder type. So hoop direction, this is basically hoop directional reinforcement. Type 3, we are using we are winding not just the cylinder part, but also this dome part as well. So this is a type 3. And this is certainly lighter than type 2 and type 1. And type 4, instead of metal liner, we are using the polymer liner, such as the HDPE or PA6 nylon liner, and then wrapped with a carbon fiber. So this density, tank density is much lighter than type 1 to 3.
From a technical point of view, 5 main factors are usually taken into account to characterize the hydrogen storage system: gravimetric density, volumetric density, operating temperature, cycle life, and system fill time. Type I pressure vessels for hydrogen storage service pressure is increased to between 15 and 30 megapascals. However, due to their low gravimetric density, they can only be used for stationary applications, especially on-site storage of hydrogen as industry gas. Under a given pressure, mechanical analysis shows that the cylinder body of a metallic pressure vessel with a homogeneous wall thickness is the weak point, where it suffers higher stress as compared with domes. Therefore, to store hydrogen at a higher pressure level, one can easily strengthen the metallic vessel by hoop wrapping the middle cylindrical portion with resin-impregnated fiber. Depending mainly on the thickness of the wrapped fiber, the pressure vessels produced thereby, called Type II vessels, exhibit the highest tolerance on service pressure. Type II seamless steel vessels with wrapped carbon fiber are designed for gas pressures of less than or equal to 100 megapascals. For this reason, Type II pressure vessels are usually used for stationary high-pressure gas storage, such as cascade hydrogen storage at a hydrogen refueling station, HRS. When the metallic or polymeric inners are fully wrapped with fiber, the resulting pressure vessels, named Type III or IV, respectively, are significantly light in weight and thus can fulfill the requirements on the gravimetric density of stored hydrogen, that is more H2 in terms of weight, for onboard applications. For the same reason, Type III and IV pressure vessels are preferential to be used in tube trailers and integrated into containers to transport hydrogen. As for low-pressure stationary hydrogen storage at refueling stations, there is increasing interest in using Type IV vessels. Although one can store the same amount of hydrogen in Type I vessels with similar investment costs, they require a larger footprint. Thanks for watching. In earlier video, we explained about classification of hydrogen storage and compressed hydrogen in detail. In this video, we will explain about liquid hydrogen storage system.
Now this is the liquid hydrogen storage.
Hydrogen in its liquid form has much higher gravimetric and volumetric density compared with compressed gaseous storage. However, the technique to liquefy hydrogen is much more difficult and consumes more energy than the compression of hydrogen or the liquefaction of other conventional gases. Liquefaction is the process of converting a gas to a liquid by modifying its pressure and temperature conditions. Cryogenic temperatures are required for this process since the boiling point of hydrogen is minus 252.8 degrees Celsius at 1 atmosphere of pressure. Liquefaction process employs a combination of compressors, heat exchangers, and expansion valves to achieve the necessary cooling. The simplest liquefaction process is the Linde cycle or Joule-Thomson expansion cycle. During this process, the gas first undergoes isothermal compression, means the temperature of the gas stays the same throughout the compression process, at environment temperature, followed by cooling at a constant pressure in a heat exchanger, and then finally an isenthalpic expansion, refers to a process where a fluid like a gas or a liquid expands without gaining or losing heat. During the last stage, some of the gas liquefies and the remainder is recirculated through the heat exchanger before flowing back to the compressor to complete the cycle. The Linde cycle works on gases, for example nitrogen, which cool as they expand at environment temperature. However, hydrogen heats up while expanding at environment temperature. To cool hydrogen as it expands, its temperature must be lower than its reversal temperature, minus 70 degrees Celsius. In order to achieve this temperature, the gaseous hydrogen is pre-cooled by evaporating liquid nitrogen to a temperature below minus 319 degrees Fahrenheit before the first expansion of the valve. Once the hydrogen has been liquefied, it is essential that it can be stored in such a way as to minimize evaporation. This evaporation of liquid hydrogen is not only a loss of the energy invested in liquefying the hydrogen, but also a loss of hydrogen in the long term, as the evaporated gas must be vented due to the pressure accumulated inside the storage vessel. This loss of stored hydrogen over time is known as boil-off and is reported as the percentage of stored hydrogen lost per day, the boil-off rate. The heat transference from the surroundings to the stored liquid hydrogen, LH2, and thus the boil-off rate is reduced by minimizing the surface-to-volume ratio of the vessels by making them spherical. LH2 vessels are usually double-walled with a gap between them. This gap minimizes heat transfer by conduction and convection. The space between the walls of the vessel may contain additional materials to prevent heat transfer by radiation. Owing to the high degree of insulation and the low surface-to-volume ratio, or owing to transfer by conduction and convection, the space.
Well, as I explained here, this liquid storage system, storage has the two wall. One is the inside and outside, and the between them is a kind of an insulation layer. Can be a vacuum or can be a multi-layered insulation. Is we need to have this insulation layer so that we can block the heat transfer from outside to inside. But as I explained here, the complete insulation is not possible, and we have to have a release system so that we can lower the pressure. So for that purpose, we have to have an extraction pipe and the several pipes inside. So this liquid hydrogen tank is not as simple as a regular the high pressure gas. But again, this liquid is much safer than high pressure tank. The pressure is only several bar, so much safer. But we have to have some real technology for insulations.
By radiation. Owing to the high degree of insulation and the low surface-to-volume ratio, boil-off rates are very low in larger spherical tanks, usually below 0.1% per day. Thank you.
The last point
and the low
they made was that so what will be the most efficient way of storing the liquid is not the cylinder type, has to be this type of a spherical type to minimize the outer surface. This is one of the points. That's why they are using this type, kind of a spherical shape to store liquid. As they mentioned, the low surface to volume ratio. What is that? Well, the sphere type is the one, the most. But volume efficiency-wise, this is not so efficient for the storages.
Volume ratio, boil-off rates are very low in larger spherical tanks, usually below 0.1% per day. Thank you.
Now, as a
In earlier videos, we explained about classification of hydrogen storage, compressed hydrogen, liquid hydrogen in detail. In this video, we will explain about cryocompressed hydrogen storage, CCH2, system. Cryocompressed hydrogen storage, CCH2, is an advanced hydrogen storage technology that combines cryogenic cooling and high-pressure compression to store it efficiently. It aims to address the limitations of traditional compressed hydrogen storage and liquid hydrogen storage by merging the benefits of both methods. Working principle: preparing the CCH2 from gaseous hydrogen requires a multi-stage compression unit with a repeated compressor and cooling system in combination with a subsequent refrigeration unit. Cryogenic cooling: hydrogen is cooled to cryogenic temperatures, typically around -253 degrees Celsius, -423 degrees Fahrenheit, close to its boiling point at standard pressure. At this low temperature, hydrogen exists as a liquid, significantly increasing its density compared to its gaseous form. High-pressure compression: in addition to cooling, hydrogen is compressed to high pressures, generally around 300 to 700 bar, 4,350 to 10,150 pounds per square inch. This further increases the density of the stored hydrogen. Storage vessel: the CCH2 vessel is in the praxis a combination of the CGH2 pressure vessel and LH2 tank. It contains in general a Type 3 pressure vessel for CGH2 that is covered by multi-layer insulation used for LH2. Among them, the vessel must be enclosed under a vacuum. Therefore, the cost of the CCH2 vessel will be much higher than that of the CGH2 vessels and LH2 tanks, and it will not be adequate for large-scale hydrogen storage. Advantages of CCH2 are high energy density. By combining high pressure with cryogenic temperatures, CCH2 achieves a higher volumetric energy density compared to conventional compressed or liquid hydrogen storage. This allows for storing more hydrogen in a given volume, making it suitable for applications where space is limited, such as in vehicles. Reduced boil-off losses: traditional liquid hydrogen storage suffers from boil-off losses due to the continuous evaporation of hydrogen. CCH2 minimizes these losses through better insulation and the ability to store hydrogen at higher pressures, reducing the need for frequent refueling. Improved efficiency: the combined cooling and compression processes can lead to more efficient storage and release of hydrogen, potentially improving the overall efficiency of hydrogen utilization in fuel cells and other applications. Versatility: CCH2 technology can be used in various applications, from automotive fuel tanks to stationary storage systems, offering flexibility in its deployment. Cryocompressed hydrogen storage, CCH2, is a promising technology that combines the benefits of cryogenic cooling and high-pressure compression to achieve high-density hydrogen storage. While it offers advantages in terms of energy density and efficiency, it also faces challenges related to complexity, cost, energy consumption, and safety. Continued research and development are needed to address these challenges and make CCH2 a viable option for large-scale hydrogen storage and utilization. Thank you.
Again, the CCH2, as shown here, cryogenic compressed hydrogen is regions over here, but practically regions over here, 300 bar, and then somewhere here, like the temperatures, which is higher than minus 253. There's a boiling off, boiling temperatures. So this is CCH2. As you can see here, the density can be now even higher than liquid. Liquid is 62. Now the density reaches the 80 gram per liter. And as you can see, we can further increase the pressure. As you can see here along this line, the temperature can be a little bit higher, but to do so, we have to increase the further the pressure. So this way we can increase the density, but the safety concern is also increased as well. So that's not the main point of the CCH2. So practically, we keep the pressure lower than 300, and also the temperature is a little higher than 253. So again, as a conclusion, the CGH2, just a regular compressed hydrogen tank, is being well developed and well used. And the liquid type, well, it's been developed and commercialized as well, but not as much as the CGH2. And the CCH2, well, technically or theoretically possible, but the commercialization is the another big problem. As explained in the video, very expensive. We can maybe find the some CGH2. Okay. We like to find some further information about the CCH2, cryogenic compressed H2. I don't know when they announced, but okay, here, 2023, about 1.5 years ago, Bonnet and Lawrence Livermore. Lawrence Livermore is one of the well famous the national lab in United States. They received some fund to further increase. And there is another announcement early this year, where this Bonnet achieved the hydrogen storage milestone, and the company founded in 2020 has made a rapid progress to develop and commercialize the CCH2. So, well, we can. So please have a very special attention to this technology and company. Bonnet, January 2024, only last year. So as you can see, this technology, this is H2, we can achieve the highest density other than CGH2 or LH2. So Bonnet was a name among the recipients, well, of commercialization support from the US DOE. United States DOE has decide to fund Bonnet to commercialize the CGH2, I mean CCH2. So again, this is a very new technology we need to understand. This can be one future method to store the hydrogen. And the Livermore National Lab and Bonnet demonstrate a highly efficient hydrogen densification pathway with a less required energy. Well, again, as you can see, very importantly, pay attention to the date when they received 2025, just 1 month ago. So Livermore National Lab, Livermore, okay, here, Livermore National Lab in California, and Bonnet demonstrate a highly efficient hydrogen densification pathway with a less required energy is an important point. As explained in the video, okay, I will get back to that video again. I hope you noticed this is a CCH2.
Buses. Traditional liquid hydrogens.
This is a boil-off. As I explained, whenever the pressure is increased, we have to release the hydrogen gas to lower the pressure. This is the procedure of a boil-off.
Storage suffers from boil-off.
And even the CCH2, we have to boil off because the temperature may increase slightly. So traditional liquid hydrogen storage suffer from boil-off loss due to, but these reduce the boil-off losses. So CCH2 have to have this boil-off, but that is the less than traditional. But still, we have to release the boil-off. What does it mean? Over the long period of time, the hydrogen gas will be released and maybe a much less than original hydrogen.
Evaporation of hydrogen. CCH2 minimizes these losses through better insulation and the ability to store hydrogen at higher.
While they are saying that this boil-off can be minimized, but what does it mean? We have to have the gas has to be released. That is not the idea for the regular fuel cell vehicles, right? Well, density is very high compared to CGH2, LH2, but unfortunately, they have to have a slight boil-off, even though for the given volume, the amount of hydrogen can be very high, which means that in the Nexo, once the Nexo fuel cell is fully charged, it can go 700 kilogram. Why not more than 700 kilometer? It is because of limited hydrogen gas. So imagine that if we have a tank which can contain more than hydrogen with the same weight, this can be increased like the 1,000 kilometers. So you can see that that can be a dream of the hydrogen vehicle. Once charged, you can you can go like the 1,000 kilometer or can be more than that. So the one of the fascinating feature of the next, this is the regular one, okay, regular CGH2. The range is achieved with a quick charge, 5 minutes. This is very important for the as a characteristics of hydrogen gas compared to a electric battery. 5-minute filling time and then done. The biggest problem with the lithium-ion or regular battery, it takes the hours to charge. Well, of course, there are recent development in the battery. They are announcing the very quick charge, but that is not fully confirmed yet. But anyhow, these are all not the new old technology. This is really brand new technology, and then we as an engineer need to understand how this further improve the technology and the we contribute to a society. So the as you can see that so the this is let's get back to the since we are studying about the CGH2, the CH2, the CCH2 truck has been developed. As you can see that once one-time charge, it can be, I mean, the distance can be about the 1,000 kilometer. Imagine that. It's a really good one. So we can uh, the driving distance on the fully charged the CCH2, okay, cryogenic compressed hydrogen tank, well, depending on the vehicle and size of so Bonnet system, for example, can enable a range of 500 miles, while 500 miles is about the 900 kilometer. Okay, 500 miles is about the 900 kilometer with a 229 kilogram tank. Can you imagine how light it is? A 29 kilogram of a tank, just two of them. So 500 miles on a class 8 truck. Even this is a truck. Uh, this is the this system is said to be 33% more energy dense and efficient than liquid. Even more efficient, can contain more hydrogen than liquid using the CCH2. And this is not the theoretical value now. This is the real applications. And so CCH2 versus other hydrogen storage, again, the CCH2 still needs to be compressed like the 300 bar in a cryogenic status. So the driving distance can be 500 miles. Let's get the precise value. Oops. So 500 kilo is the 500 miles about the 800 kilometer. And other factors, factors like driving style, road condition, and of course, it depends on other factors. Again, the good news is that this ideal the efficiencies now commercialized and price is really high, but always the price will go down as a demand is increased. So that is the what the and why engineers contribute to our society. So anyhow, is important. Let's see what it says. While the just a regular passenger vehicles is not so appropriate, then truck. A truck is the ideal case, ideal applications of the CCH2. So the well, how long is this video? Well, sorry, let's move on. So it is important to understand the CGH2, LH2, and CCH2, okay?
Pressures, reducing the need for frequent refueling. Improved
Okay,
efficiency.
well, let's have a 10-minute break. It is a 4:10. Let's come back to 4:20. Thank you.
Combined cooling and compression processes can lead to more efficient storage and release of hydrogen, potentially improving the overall efficiency of hydrogen utilization in fuel cells and other applications. Versatility. CCH2 technology can be used in various applications, from automotive fuel tanks to stationary storage systems, offering flexibility in its deployment. Cryocompressed hydrogen storage, CCH2, is a promising technology that combines the benefits of cryogenic cooling and high-pressure compression to achieve high-density hydrogen storage. While it offers advantages in terms of energy density and efficiency, it also faces challenges related to complexity, cost, energy consumption, and safety. Continued research and development are needed to address these challenges and make CCH2 a viable option for large-scale hydrogen storage and utilization. Thank you.
The CCH2.
In addition to the physical-based hydrogen storage technologies explained in previous videos, there has been an increasing interest in recent years in storing hydrogen by chemically or physically.
As we noticed here, Bonnet announced that the product using the technology of a CCH2. Well, I wonder any further information of their technology. Okay, this is the tank. Looks like a regular pressure tank, wrapped with a wet winding tank. So Bonnet's breakthrough technology. Bonnet currently leverages state-of-art compressed hydrogen technology, but this is not just the compressed, but also cryogenic inside. So their visions is today 2020 versus the future after 10 years, 2035. As you can see that the cost will be much less than diesel cost. Now the battery and the well, diesel cost is a kind of a reference cost to compare with, and the battery and the bonnet is higher than diesel cost. But after 10 years, the price will goes down. The main problem with the CCH2 is the cost. The But once these technologies are fully developed, the well, I don't know what is this, but the charging time is a much competitive than any other the method. Like we can compare the okay, CG H2, just a regular compressed H2. The charging a battery in an electric vehicle takes the several hours, as we know, but filling a hydrogen tank in fuel cell takes several minutes, very similar to the getting the oil and gasoline. And the so the battery charging, while this is another topic we need to understand, we as an engineer also like to improve the or shorten the time of the battery charging time, and the hydrogen refuel CGH2 and LH2 and all kinds of method can be compared. Well, battery has several issues. One of the issues is the charging time. Uh, as we, I'm sure you heard this story. There are very quick charge technologies. Oops, this is not. Mm. Quick charge battery technology for electric vehicles is increasingly commercialized. Okay. This is the one of the most severe drawbacks of the battery types for electric car. Again, the conventional, it takes the several hours, but recently BYD announced that very fast, even faster than just a fast, flash charging battery technology, and the very short charging time. How short? Well, 5 minutes to reach the 400 kilometer of range. really, this is a super fast. The ultra fast charging, Shenxing technology allows for 520 kilowatt range after 5 minute charging. This is amazing. Why this technology is so difficult? Well, the battery is not like the mechanical movement of energy. Is a chemical reaction inside the battery. So, for example, the lithium ions have to move. So chemically, it should take some time, so hours and hours. But right now they are okay. Let's take a look at the okay. Let's take a look at the our current news. China's ultra-fast electric vehicle charging technology outpaces U.S. competition. While there are a lot of competition between China and United States, but in terms of these fast charging electric vehicles, outpace United States. So the world largest motor show. Oh, that there was a motor show in the in China, where it was just several weeks ago, right? Shanghai Motor Show. I remember that this was just 2 weeks ago. When was it? Yeah, I remember so the CATL, according to Chinese media, the CATL, one of the largest battery company, world's largest electric vehicle battery manufacturer, unveiled its second generation of a battery, Shenxing, which is capable of ultra fast charging. So it's amazing technology, just the 5 minutes, and reach a drive of 520 kilo. Even this news has been released in CNN. 5 minute charging go to 250 miles. 250 miles is about the 400 kilo. These Chinese electric vehicles, BYD, this is a vehicle company, but the technology is a CATL, I guess. I like to understand the BID's fast electric vehicle charging technology, particularly their Super E platform, relies on combination of a high voltage system. Okay, this is the one of the technology they are using, high voltage system, advanced the battery technology and powerful charger. We have to have a charger as well. The charger means that you have to have a power, a lot of high power charging system to achieve ultra faster charging speed. vehicle to add significant. BYD says that super fast. BYD. Okay, let's take a look at this one. Well, we are studying about the hydrogen energy system, but in parallel, we need to understand the technology of a battery as well. The battery itself is a really important subject we need to understand. BYD, 5-minute electric vehicle.
Insights into this industry. How significant is this BYD claim then of a 5-minute
This is a Bloomberg
charge for the industry?
Yes, so BYD have announced that their newest EV platform is going to be capable of charging at up to 1 megawatt of power, which is really an unprecedented jump forward for the passenger vehicle market. That higher peak power is one of the elements facilitating these charging times that are comparable to petrol refueling. And if we compare it to what else is on the market, that's more than 4 times the peak power that a Tesla Model Y can pull.
Wow.
And in China, even premium trims on something like the Xiaomi SU7, which has been touted for its fast charging capability.
Okay, well, pay attention to this chart. Very nice. The Tesla Model Y performance 75 kilowatt hour. Let's say this is the what range. Just the comparison, 5 minutes charging. How much range we can drive? 5-minute charging. Okay, just a 5 minute. Now the Tesla we can reach the 100 kilo. Now the Porsche and Xiaomi and BYD can reach the 400. This is the really fantastic technology. I like to copy these things. Troubles. Okay.
Have a peak power of around 500 kilowatts. So BYD really has crushed its competition on this peak power point. But to charge at that speed, you need to be connected to a charger capable of delivering 1 megawatt of power. And that doesn't exist in the public network at present. So BYD have announced in China they're going to build 4,000 of their megawatt flash charging stations. The first of those are going to be ready as soon as next month, which really highlights the pace at which they're moving with this technology. But that isn't going to touch the sides of China's 3.6 million public chargers that is already installed and can't necessarily deliver this power. Probably also worth flagging, you need to be plugging in a very low state of charge to pull that megawatt of power and achieve these really super.
So anyhow, the point is that how they achieve, what kind of technology do they have, BYD, to reach that, the super fast? Well, I'm sure that not the detailed technology has been released, but let's go to ChatGPT says, let's see what oops. Okay, well, I can just copy this one. In that news, they are just mentioned that I just copied this one. Okay, let's see what that says. Okay, This image shows that this is ChatGPT, shows that BYD Super E platform has nearly 4,000 meters of range in just 5 minutes, and compared to Xiaomi and Porsche and then Tesla. Here's how BYD may achieve this. They said may is kind of a guess by collecting all the informations available in the public. So ultra-fast charging architecture. BYD Super E platform likely use high voltage architecture. See, high voltage is one way to achieve possibly 800 volt or more, or really super high, which allows a significantly faster energy transfer rate. This charging power could exceed 600 to 700 kilowatts. This is a really super high power. And typical value is about the 200 or 300 kilowatt public charger. What does it mean? The public charger, we need a very special charging system. And second, advanced battery chemistry. This technology possibly integrate, they said possibly, they are guessing, integrate the next generation lithium ion LFP, phosphate, LFP is very well known, or blade batteries with a better thermal control and lower internal resistance, allowing high C-rate charging, fast charge without overheating or degradations. Okay, so this may also be a dual chemistry or segmented batteries optimized for rapid initial charging and efficient thermal management. While all the battery has the battery managing system, BMS, I guess they are using the very efficient thermal management and also a powerful energy, yes, BMS here, and thermal management. All the power energy transfer relate to heat generation, how carefully or effectively the managing the thermal point is a really important aspect. Optimize the drive system, high energy efficiency in motors and where drive train well optimized. Real world considerations. Okay, number 4 and number 5 is important, but not the major one. And 3 is the important, but not the major. The number 1, ultra fast charging architecture is not the vehicle, is a charging station. So we need a super high charging system. One of these ultra fast charging system is the flywheel system. Flywheel is the can release the very high power energy than any other charging system. And the most important point is the advanced battery chemistry. As I mentioned, the battery, lithium battery or LFP is always the chemical reaction, which has to take time. But let's say what they're saying. To understand this point, advanced battery that could explain how BYD Super. Okay, let me remind you that why we are paying attention to charging time is that the biggest advantages of a hydrogen tank or storage is the fast charging, like the 5 minutes. That used to be a very important point compared to a battery. Now, battery technology has been getting better and better and improved. And then we need to understand how the battery can even can be developed in a way to kind of a faster charging. So, well, this is the important aspect. Anyhow, advanced battery chemistry in BYD fast charging is the blade battery, LFP-based, patented by BYD. One of the BYD major innovation in the blade battery is a re-engineered lithium ion phosphate LFP cell design, high safety. Yeah, LFP is known as very safe, safe than NCM, nickel chrome mangan based battery, very high safe. And the long cycle time means that charging, discharging, charging, discharging, 3,000 plus a cycle. Well, one cycle is considered as the within 80% of charging capacity. So 3,000, for example, if you daily charge is 365 days daily charge, it can last about 10 years, even daily charge. So if you weekly charge, then it can last 70 years. So improve the volumetric efficiency, ultra fast blade shaped, high C rate, and important hybrid anode and cathode materials. BYD used the advanced cathode. You know, the older battery, even for the hydrogen storage or fuel cell, we always have the cathode and anode materials. So BYD use advanced cathode material. High lithium ion diffusion rate, low resistance coatings, carbon ceramic coatings. They could also explore hybrid battery packs. Hybrid means that the fast charging section for quick burst. Okay, the NMC or NCM or lithium titanate high energy section for the sustained ranges. Okay, maybe a combinations of NCM, NMC, nickel mercaptan. This is a fast, high density, high charging, and the high energy. Okay, what does it mean is that LFP is known as the high energy section, and NMC is known as a fast charging. So they are combined two technology, solid or semi-solid electrolyte. While the regular battery is the liquid type electrolyte, but this is the solid electrolyte and thermal structures and so on. Well, I can see that there are some technologies being gassed. I mean, it's not not full technology has been released. Okay. Yeah, it described the blade technology as the number one factor which advanced the battery chemistry, while others are kind of combinations, but the blade looks like a very new one. So I asked for the information of the blade battery. Let's delve deeper into the blade battery technology, which plays a pivotal role in lithium-ion phosphate LFP chemistry and innovate blade cell. Okay, I guess the one of the most important point here is the blade technology. While this is first time to me as well. Okay, where did this go? Battery. Looks interesting. Blade battery comprehensive guide. Okay, again, this really new technology and the main technology to makes this possible is that this BYD blade battery technology, and I guess it's important to understand this one. Again, why we need to pay special attention to fast charging is that one of the biggest advantage of a hydrogen tank is the fast charging. Now, even battery overcome this technological barrier. Anyhow, let's move on to our next topic. But it's important to understand both battery, lithium-ion battery, and also along with this understanding of hydrogen tank. Okay, let's get back to let's continue to other system. Hydrogen storage part 4, liquid organic hydrogen carrier. Okay, LOHC is a very common word right now. Liquid organic hydrogen carriers.
Combining it with appropriate liquid or solid materials, material-based hydrogen storage. Liquid organic hydrogen carriers, LOHCs, are one type of promising material for this purpose. At ambient temperatures, they are liquid or semi-liquid organic substances and contain unsaturated bonds that enable them to store hydrogen molecules through a chemical reaction, hydrogenation in the presence of catalysts. In the process of hydrogenation, hydrogen is chemically bonded to the LOHCs. The LOH, in its dehydrogenated form, for example, toluene, is reacted with hydrogen under high pressure and temperature in the presence of a catalyst. This reaction converts the LOHCs to its hydrogenated form, for example, methyl cyclohexane for toluene-based systems. This hydrogenation process is typically conducted at temperatures between 150 degrees Celsius and 300 degrees Celsius and pressures between 30 and 50 bar to release the stored hydrogen. The hydrogenated LOHCs is heated in the presence of a catalyst.
Well, the basic idea of this LOHC is that if we have a hydrogen, molecules, and combined with the LOHC, with the pressure and the temperature, with the catalyst, this is an important, plays a very important role. And then there is a heat generated. And then once we kind of chemically combined, HN, LOHC, is a pressure is just a regular pressure, 1 to 5 bar, much safer with the high temperature. Now we have to supply heat to release to get the H2. So with this when we carry or store, we using the HN LOHC, and whenever we need a H2 back, we add heat here. It's much safer, but as you can see, we have to have a heat in and out depending when we convert in these conversion procedures. So heat in and out means that energy loss. But again, this way it is gonna be very safe.
The dehydrogenation process reverses the hydrogenation, releasing hydrogen gas and converting the LOHCs back to its dehydrogenated form. This process typically requires temperatures between 250 degrees Celsius and 350 degrees Celsius. LOHCs are non-toxic and non-flammable, making them safer than compressed or liquid hydrogen storage methods. They can be handled similarly to conventional liquid fuels, reducing safety risks. LOHCs have a high hydrogen storage capacity, enabling the storage of significant amounts of hydrogen in a compact form. Challenges such as hydrogenation and dehydrogenation processes require significant energy input, which can affect the overall efficiency of the system. The cost of LOHCs, along with the energy and infrastructure requirements, needs to be competitive with other hydrogen storage and transport methods. LOHC's technology represents a versatile and promising approach to hydrogen storage and transport, addressing many of the challenges associated with hydrogen as an energy carrier. While there are still technical and economic hurdles to overcome, ongoing research and development efforts continue to improve the feasibility and efficiency of LOHC systems, potentially making them a key component in the hydrogen economy of the future. Thank you.
Well, as shown here, these LOHC types of is storing H2, because H2 and LOHC chemically combined, and they're much safer. And then it can be used for of course, the storage, or can be used as transportations of the H2. But in a large volume, not the small volume. Small volume is cost will be much higher increase. So kind of a large volume application, this been already developed and then been used.
Systems, potentially making them a key component in the hydrogen economy of the future. Thank you.
Now this is the last subject, like the metal hydride. Let's take a look at.
In previous videos, we have explained about different hydrogen storage system. In this video, we'll explore a unique class of material-based hydrogen carriers, available in both gaseous and liquid forms. These carriers can store hydrogen molecules and release them on demand while also being usable as fuels. With impressive volumetric storage densities, ammonia at 17.7 weight% and 123 gram per liter, and methanol at 12.5 weight% and 99 gram per liter, they offer relatively low energy consumption and simplified hydrogenation and dehydrogenation processes.
Sorry, this is not the solid type.
However, most power fuels aren't economically viable for use as hydrogen carriers. Independent of its chemical composition, a suitable hydrogen carrier must provide a sufficient hydrogen capacity, greater than 5 weight%, easy and environmentally friendly production process, not too harsh conditions and high stability during storage, easy and safe handling during transport, low energy consumption during hydrogen release, option to be recycled. Ammonia. Ammonia can be decomposed into hydrogen and nitrogen gases through a catalytic reaction. Two ammonia molecules under catalytic reaction will produce 3H2 and nitrogen. While storage and transport of ammonia are well understood, releasing hydrogen from ammonia remains a significant challenge. The decomposition reaction is thermodynamically favored above 400 degrees Celsius, but it faces kinetic limitations due to high activation energy. Current research is focused on developing catalysts that can operate under milder conditions by optimizing their composition, morphology, and interactions with
While
the
using the
materials.
ammonia to
Although
carry
catalysts
as a carrier
decomposition
is a very well-known technology nowadays.
and
Also, this
performance.
technology is being used for the
The process of storing
mass
hydrogen
carriers
in the form of methanol
and also
occurred
methanol
in
reforming
the
procedure as well.
20th century, where carbon dioxide is hydrogenated on the surface of copper-based heterogeneous catalysts. Compared with other catalytic reactions of methanol to release hydrogen, methanol steam reforming is the most favorable because of its higher hydrogen yield per methanol molecule and relatively lower energy consumption. Advantages: ammonia and methanol synthesis are two well-established chemical technologies. Given their high energy densities, these chemicals can store a large amount of energy in a small volume, making them more efficient energy carriers than gaseous hydrogen, which has a low energy density. Ammonia and methanol can be transported on a large scale using existing storage and transportation tools. Methanol, being in liquid form at room temperature, is safer to transport than gaseous hydrogen. Additionally, ammonia and methanol are less flammable than hydrogen, reducing the risk of accidents during transportation and storage. Compared to hydrogen, methanol and ammonia are easier to store.
While as a result, the ammonia hydrogen carrier is much easier to store. Obviously, at the room temperature, hydrogen can be stored together with the ammonia or methanol. But especially ammonia has been used for the rear transportation. But as you can see that ammonia has to be, this is methanol. Well, ammonia now has the nitrogen and hydrogen. So the hydrogen can be carried in terms of ammonia. So as you can see, we have to have a conversion procedures to use the hydrogen. But there is a recent technology. ammonia can be used directly as a fuel for transportation. What does it mean? It means that really a breakthrough is just a fuel as a fuel, ammonia in, and then you can run the fuel cell vehicles rather than high press gas. So this is the ammonia can also be used as a fuel cell. This is a hydrogen carrier, ammonia. I guess the startup, there is a startup company. Yes, a transportation startup company, Amoji, is using the ammonia as a fuel source. Can you imagine that we are using the ammonia as a fuel source? Ammonia, again, is very safe, and then we can carry them at the room temperature. This is not the liquid type, so we don't have to keep them cool. We don't have to press high pressure, just ammonia itself. And then inside is breaking down into a hydrogen, nitrogen. This Amoji is the company, startup company, and they developed. We build the technology that unlock ammonia's potential as the clean energy source, accelerating the global journey, net zero. While let's take a look at this ammonia to power. Well, it is a 100% carbon-free electrical power. Let's say, okay, let's take, okay, fuel cell arrangement. Our fully integrated power system deliver carbon-free ammonia power, while the so Amoji, let's go to here. Amoji is the company, US-based startup founded in, again, it's not long ago, just 2020 by MIT alumni. It's a pioneering Nobel system. Okay, how it works? Well, we don't want to go in detail, but the point is that they just use let's just browse it. Their technology focus on converting ammonia into a hydrogen on-site. Okay, this is an important word, on-site, which is then used to generate electricity through a fuel cell. And they got a lot of money investment from Hanwha and the JGC Holding. they got a lot investment. As I said, this is the startup company only 5 years ago. On January 2025, this year, Amoji has raised over 270 million dollar in total funding to advance its ammonia to power. Okay, this is not the hydrogen power, just ammonia to power. And then, the Aramco is the one of the another investor as they also invest. So the Hanwha and so on. Now this Amoji was founded a team of MIT PhD in chemical engineering and so on. Now, as you can see that they are all Korean guys, Lee Jae-hyuk and Kim Young, and all the Korean guys. So they are Korean MIT guys, and then they start up the company in United States. That's why the Hanwha got invest a lot of money, and not just the Hanwha, but also other company like the Aramco invest a lot. So this is really promising technology that it solved a lot of issues like the safety issue and also the density issue and so on. What are the biggest barrier in this technology? But it faces several major barriers before it can be achieve a large-scale adoption. Well, as he said, is a really groundbreaking technology. Oops, sorry. It faces several major. It can achieve a large. These challenges span across some biggest barrier: ammonia cracking efficiency. The cracking means the inside. Once ammonia in, ammonia has to be cracked down. Means that we have to break cracking nitrogen, hydrogen. There we have to have energy in there. So there is a concern about the efficiency and the safety concern with the ammonia. Well, ammonia is safe in terms of pressure or temperature, but ammonia can be a very toxic, a chemical toxic, and very strong odor, smells, and so environmentally, this been is categorized as a toxic chemical. Not so much toxic, but handling and transport and onboard requires a very specialized equipment. And there are several other issues, lack of ammonia fuel infrastructure. Always once new technology comes out, the infrastructure has to be established. But it's a very early stages. So we don't have enough infrastructure yet, and cost and commercial viability. Well, Amoji's system currently involve high cost custom component and so on and so on. But nevertheless, this technology really promising, and then we need to understand the concept, and while we can learn from this idea and technology. Okay, so Amoji is company, and we need to understand Okay, this is the methanol and ammonia as a hydrogen carrier. Okay, this is the video.
At critical considerations. The choice between the two depends on specific requirements such as storage conditions, hydrogen release rates, and environmental impact. Thank you.
Oops.
In addition to the physical-based hydrogen storage technologies explained in previous.
Now let's take a look at the solid metal hydride. Okay, here is the metal hydride.
Transporting
there are now this is a physical base. I mean the inside the metal hydride, the gas will smear into metal hydride solid. Let's take a look at
energy carrier. Metal hydrides are compounds formed when hydrogen reacts with metals or alloys. They can absorb and release hydrogen gas under certain conditions, making them useful for hydrogen storage applications. Key concepts of hydrogen storage in metal hydrides. Formation of metal hydrides. Metal hydrides are formed through a chemical reaction between a metal or alloy and hydrogen gas. Reversible storage. Metal hydrides can reversibly absorb and desorb hydrogen. This means they can store hydrogen by forming a hydride and release it when needed by breaking down the hydride.
Well, obviously, this is just a metal crystal. You know, the older metal has a crystal in there. Now these H2 molecules, H2, and go inside this crystal. So we call metal hydride. And absorption procedures and desorption procedures. So with this metal hydride, while this metal crystal contains this H2 in very safe way. So this is just a metal, and then at room temperature, and also regular pressure, ambient pressure, we can store or carry this hydrogen in a metal. But the disadvantage will be kind of too heavy because of this is a metal, and there is the procedures of absorbing and the dissolving procedures.
Process can be represented as. This reversible process is crucial for practical applications, such as hydrogen fuel cells, where hydrogen needs to be stored and then released on demand. 3. Thermodynamics. The absorption and desorption of hydrogen in metal hydrides are governed by thermodynamic principles. The enthalpy change, delta H, and entropy change, delta S, of the reaction determine the temperature and pressure conditions under which hydrogen can be absorbed or released. Metal hydrides with lower delta H require less energy to release hydrogen, making them more efficient for storage applications. Types of metal hydrides, intermetallic compounds. These are compounds formed between two or more metals, such as lanthanum pentanickel, LaNi5, and magnesium hydrides, Mg2Ni. They are commonly used in hydrogen storage due to their favorable hydrogen absorption and desorption properties. Complex hydrides. These include materials like sodium alanate, NaAl4, and lithium borohydride, Li4. They can store a higher density of hydrogen but often require catalysts or specific conditions to release hydrogen. Carbon materials. Examples include graphite and CNF, which can absorb hydrogen at higher capacity. Hence, in order to obtain a relative higher gravimetric density, the selection of storage materials has to be restricted to the light solid elements. In addition to considering the storage density, high hydrogen density, metal hydrides can store maximum up to 7% hydrogen at a higher density compared to compressed gas or liquid hydrogen. Safety. They offer a safer alternative to high-pressure gas storage. as the hydrogen is chemically bound in the solid phase. Reversibility. The reversible absorption and desorption of hydrogen make metal hydrides suitable for applications like fuel cells and portable power systems. Challenges include weight and cost. Some metal hydrides, particularly those involving rare or heavy metals, can be expensive and add weight to the storage system. The rate of hydrogen absorption and desorption can be slow in some materials, requiring catalysts or specific conditions to improve performance. Applications includes metal hydrides are used in hydrogen storage for fuel cells, portable power systems, and hydrogen compression. They are also being explored for use in hydrogen-powered vehicles and renewable energy storage systems. Research in metal hydrides focuses on finding materials with higher hydrogen storage capacities, faster kinetics, lower costs, and better reversibility. Advanced materials, such as nanostructured hydrides and complex metal alloys, are being explored to overcome current limitations and enhance the efficiency and practicality of hydrogen storage in metal.
Okay, well, this is the new technology which is being developed and for full commercializations. As far as I know, it's not been fully commercialized yet, but also this is very promising technology because mainly due to its safety and also I mean safety point of view and temperature and pressure. But the biggest barrier is very heavy to carry as a carrier of the hydrogen gas. So we have to look for the advanced material, the solid, such as a nanostructures hydride and the complex metal alloy, or we can invent certain types of a metal alloy and are being explored to overcome current limitation and so on. So as you can see that the hydrogen carrier like nitrogen and also metal hydride is very promising technology to store hydrogen, but not as much as commercialized as the gas type, the tank type or liquid type. But we have to go, all the technology always move toward safety and more higher efficiency. So why? Because that's a demand. There's always a demand by the customer or our society want that. So we fully understand the ideal directions, and then we can get visions, and we engineer develop those technology, and that's how we contribute and return. You guys as engineer can get a lot benefit in terms of you can be rich, you can be famous, like the Amoji. That company is a startup company. 3 Korean guys, startup company. Their vision started from their technology, started from their visions. How can we make this safer and the more? How to carry the hydrogen? Well, ammonia is as input rather than high pressure gas. And then we get the energy out directly from ammonia. That's a really ideal case demanded by the society. Now, engineer develop the technology to realize that dream. And I also like to understand this metal hydride. When can it be commercialized? We don't know yet. Maybe we can ask. Well, let's ask ChatGPT, when can the metal hydride be fully commercialized? Let's see what it says. The full commercialization of metal hydride-based storage depends on the solving several key technology and economic challenges. So the application area, small portable device, already been commercialized by this 2025, and backup power as a backup power system, meaning that we need to store as energy as a backup, and this passenger vehicle cannot is not developed yet for the passenger vehicle in by 2025 this year, not viable yet due to weight. It's gonna be too heavy, too big. So unlikely before 2020, 2030. Well, this is the important point. See, if you guys are interested in this metal hydride, and the I will pay more attention to passenger vehicle applications. Even ChatGPT says not viable, but this is the we can be smarter than ChatGPT. So anyhow, well, I don't want to challenge them, but the heavy duty experimental pilot. You see, this is a heavy duty truck. So 2027, 2032, from 5 years from now on, can be kind of commercialized. And the why commercialization is slow? Well, pros and cons of hydride, metal hydride, high volume and high density, too heavy, very so barrier weight is a big barrier, and the temporary requirement and so on, so on. So the it's important to understand the each characteristics of storage technologies. While they suggest that, would you like a comparison chart between metal hydride and other hydrogen storage methods, such as the compressed gas, ammonia, ROHC? Okay, let's see what it says. Comparison chart. Chart is just a table. Hydrogen storage technology comparison. That storage form, solid. Now, as a conclusion of this all studying the hydrogen storage methodology, we like to compare them. Each one has the pros and cons and so on. So the to better understand, we can kind of have this kind of table. Storage form. Okay, this is the one, it says solid metal hydride, and the pressure. Okay, this is a metal hydride aspect, and here, this is the compressed gas, and here is the liquid. Here is the ammonia, and here is the ROHC. So I hope that well, this is the kind of a conclusion of these sections of the hydrogen storage methodologies. We compare the metal hydride, compressed gas, liquid. Well, there was CCH2 as well, and ammonia and LOHC. So liquid type, this is the gas type or liquid type, and this is ammonia as a hydrogen carrier, and LOHC, and then also metal. And this can be important point. So I hope that you go through this table. Again, you can have your own table. I mean, you don't have to look for the older items and characteristics. You can discuss with the ChatGPT or Google or so many research which can do for you. But the point is that we should understand each technology and the visions and barrier, and then there are always chances for engineers. Chance means that for your own good and for the in terms of a contribution to a society. Okay, well, was trying to cover all the hydrogen storage methodology in today's class. We didn't cover them all, but I just introduced the technology and together with just a little bit of a battery, the battery understanding of how the energy are stored in the battery, like a lithium-ion battery, is also a big subject and so important subject. I hope that you guys study more and compare with the hydrogen energy storage system. Okay. Okay. So our class is finished now, and then thank you, and see you next week. Again, sorry for no time for the feedback. If you have any questions, then please feel free to send a message through our catalog and even email or anything. Again, all the video, our lecture note today's will be saved and then shared through YouTube. Thank you. Bye.